We've got Long Lee here to talk about ARM Exploitation ROPMAP.
Thank you. Good afternoon, and thank you everybody for coming. I am Long Lee, and my co-presenter unfortunately cannot show up due to his sickness. We are really sorry about that, and I will do it myself. So this is the last talk of today. We were talking about return-oriented programming on ARM architecture, and we will talk about automatic payload generation for ROP payload on ARM architecture. So just a quick introduction. We are from VN Security Research Group from Vietnam. And actually our research is just our opinion and not represent any opinion of our employer. Okay, so why is this talk? People now familiar with the term ROP, or return-oriented programming. In this talk, we will cope with three problems. The first one is the ROP toolkit for ARM architecture. So you know that today ROP is a must-use exploitation technique to bypass non-executable protection like DEP or NS. And there are several ROP toolkits for x86 architecture, like, you know, DEPLib from Immunity, you know, Mona from Golang Bear team, and other tools like Skyrack. But actually, there is no such toolkit for ARM architecture, or no public toolkit. And one of the problem with the x86 ROP toolkit is stick with the x86 dependency, like it rely on Immunity debugger backend. So in order to port that toolkit to support ARM architecture, it will not be easy and will take time. And people may argue that with just object DOM and grep is enough for them to construct ROP payload for ARM architecture. It's true. You can have a look at Cormac jailbreak framework. So he just use Auto and grep to find the gadget. But it will be take time to construct the ROP gadget like that way. And it will be hard to do automation with just grep. The second problem we cover with about the ROP shellcode. So you know that if you have a chance to look at ROP shellcode or payload from public exploits, like Sayonara payload, like JailbreakMe payload. So you see that all of that ROP shellcode and payload are hard-coded in terms of like instruction of the gadget, in terms of register you're using, and in terms of the offset. So all are hard-coded, and it cannot be reviewed. It will be very difficult for people to, let's say, to understand, to maintain. And unlike the traditional shellcode, ROP shellcode is not like write one and use many times. It's write one and use one because it depends on the module and the library. So when you upgrade the library to a newer version, you cannot reuse the old shellcode. So we actually need a way to write ROP shellcode in easy manner and portable, maintainable. The third problem we come with is doing ROP automation. Anybody here attend last year presentation about this topic? It's called Everybody Become the ROPery from Vincenzo Ozo and his colleagues. And so you will see that in his presentation, he do some ROP automation with solver and write language a lot. But from my observation, from practical use, that COMAC star framework with just simple gadget can beat that automation tool in terms of time to deploy the exploit. So one thing we copy here is, in order to do the ROP automation, an important note is we can just only need to use simple gadget instead of try to find complex gadget. So in this talk, we will present just three things. First one is how to extend an available x86 ROP toolkit to support ARM architecture. Second one is we will present an intermediate language for ROP shellcode writing. So you now have an easy way to write ROP shellcode and get it, convert it to the payload automatically. And the third one, we will show an implementation. We can call it an ROP assembler to assemble the ROP shellcode to the payload. And that is one of our implementation. From what we presented here, you can build your own toolkit by what we saw today. So now, the first part, yet at the end, by the end, you can see on the screen from the left, you will have a way to write ROP shellcode in easy manner. So you can see that the ROP shellcode is easy to understand, short, clean, and then it can be transferred to gadget chain automatically, and that depends on the architecture here for the ARM architecture. And finally, we have the payload for the exploit automatically. First, we'll show how to extend available x86 ROP toolkit to support ARM architecture. So if you are writing your own toolkit, this information may be helpful, and even you are just user of available toolkit, the new toolkit, it's good to know that. From x86 to ARM, there is some difference you must know in order to use or build the toolkit. First, we talk about register. You know that ARM architecture is a rich architecture, so they use lots of register. For x86, we have some general purpose register like AIS, ABS, and in ARM, we have equivalent. It's named R0, R1, R3, etc. That is general purpose register, so you can use for like function argument or for data exchange in assembly. There are also some special purpose register that is reserved permanent for like a stack pointer, ESP, and in ARM we have SP. Like program counter in x86 we have EIP, and in ARM we have named PC. For the frame counter EBP we have equivalent in ARM is the FP, and there is another register that is not available in x86, that is link register, which will contain the return address after when calling the function. About the assembly, we just show here some common use assembly instruction on x86 and equivalent in ARM architecture. Most of the instruction here is used in exploit writing, so just common one, not on. We just show the common one. The first one is load value from the stack. We both have the pop instruction in both architecture, and in ARM architecture, it's also support. It allows you to load to pop many registers in one instruction, like just pop R2, R7, and even PC in just one instruction. For data movement, we had the move instruction, same into architecture, like move from a register to another register. Arithmetic operation, we have the same instruction, add and sub, like add a register with a value or sub a register with a register. For data movement, they are a bit different. In x86, we just have the move instruction. So it just move value from memory to register or vice versa. But in ARM architecture, there are two different instructions. It is LDR for load a value to register, and STR to store the register to memory. For calling function, we have a call instruction in x86. In ARM, we have BL or branch with link. So return address will be loaded in the link register. For indirect call and jump, we have the instruction is BLX or BX corresponding. So for the rest instruction from return from the function call, we have in ARM it's a pop PC BXLR just jump to the link register, or even you can do like move PC with a value directly. And another interesting instruction for writing shellcode is a syscon. It is interrupt, like in x86, it is interrupt 80 hash, and in ARM we have equivalent a supervisory call at VC. So that just some simple and common assembly instruction in both language, so you can catch up. You're familiar with x86, you can catch up with the ARM assembly quickly. How about writing the shell code? So we have it is similar in both platforms. In x86, we just load the EAX with syscon number, and in ARM, we load it to register 7 or register 12 syscon number, and argument go to all the register. Then we issue a system call. For ROP gadget, so on x86, we looking for the red instruction. In ARM architecture, equivalent is pop something, then PC. It can be treated as a red. BSLR, jump to the link register. For example, in x86, a very common ROP gadget like pop red. So in ARM, it's just in one gadget. It is pop, L1, L2, and PC. So it may be different. And for indirect gadget like return in con EAS or jump EAS, we have in ARM a BOS, a register, or BS to register. Note that for x86 architecture, there are no alignment of the instruction, so you can find a lot of gadgets from unintended code, like something the code is just do data movement, but by shifting every byte, you can find interaction gadget. In ARM architecture, there's a bit different. Instructions are on alignment by every 4 byte or every 2 byte. It depends on the ARM mode or thumb mode. So most of the gadgets on ARM you can find from intended code. So that's why object DOM or O-Tool will work for you. So in order to find the gadget, the algorithm will be the same as in the x86. You just search for a red equivalent instruction here, like pop something PC, and for indirect return gadget like BS or BOS to a register. So we have the code represented in the Python regular expression format. So just need to find a rest line instruction. Then we will disassemble backward every 4 byte for ARM mode or every 2 byte for thumb mode. And we will stop when there is an invalid instruction or we read the depth we control. So it's the same. The algorithm will be the same. And you can use your own disassembly library. From public, I know that there are just a few disassembler libraries support ARM architecture. And in our implementation, we use RADAT tool with Python binding. So we have a quick demo here. We will here the tool ROPME, which is the first public ROP toolkit released last year in this conference, and now we extended to support ARM architecture. And we can generate for the gadget. So just that a few minutes to generate the whole gadget for libc of Android platform. warp, maybe too big. So I will back to here, just assemble a gadget. So with the tool now, you can search for the gadget easily. It must be more convenient than grab with plain text. Here, like example, for example, you can search for pop R0 instruction to find what gadget will load register R0 from stack. Or you can search for the gadget that load register R0 from another register reference. So, okay, 1 minute to generate the gadget. Now you can search for like so you have a list of gadgets for use. And now if you are satisfied with that, just it's okay. You can go and build your ROP exploit with that tool. It's now available for you to use. But it will take you a lot of time to write the shell code and the payload. And what we intend to present today here is a way to do it automatically, so it can save you a lot of effort in exploit development process. In the next, we will present an intermediate language for ROP shellcode writing. So you can write the ROP shellcode an easy way. You can get it compile or assemble to the payload automatically, and that shellcode will be, let's say, easy to understand, easy to maintain, easy to implement yourself if you want to build your own toolkit. For here, an example of ROP shellcode extract from the JailbreakMe framework. So for practical ROP payload, in common payload, what they do are just chain many library calls together to bypass non-executable protection. Or they just disable non-executable protection with ARM protect, virtual protect, something like that, and then transfer the normal shellcode to target memory, and then just execute it. And from our observation, common operation for ROP shellcode is just involved in register assignment. So just load register with value, and data movement, like something you want to make a parallel stack for your data preparation purpose. So you just need data movement instruction. And finally, making call to function call or system call. And that's enough to write the ROP shellcode. So we introduce a language to write the ROP shellcode. It is just a simple procedural assembly language. So everybody is familiar with assembly, so we make it like assembly, so people can learn it easily. It contains only 6 instructions, very small instruction set, so you can remember it. And we do not invent new register name, so just define the instruction, and you would use the native register from the platform. Like for x86, we still use EAS. For ARM, we still use R0 or R2, R3, like that. So if you have something to remember from presentation today, just need to remember this slide. So we introduced the ROP intermediate language, which is 6 instructions. It can load, store, adjust, con, and syscon, and not no operation. So the 6 instruction in the form that instruction left-hand side operand and right-hand side operand. In that the left-hand side is the destination and the right-hand side is the source of the instruction. And for the left-hand side and right-hand side data type, we have 4 types. It's the register, value, constant value, memory reference by a register, and memory reference by an address. That's all. So I will show some use of the instruction in detail. First instruction and the most common use instruction is load. So to load a value to a register, the left-hand side must be a register, and the right-hand side can be in any type. So we have here, for example, a load register 0 with the value cafe baby. Every constant value will start with a common symbol. And load register to register, load register from reference, memory reference, and to most use instruction you can find in the shell code load register with value and load register from a memory reference. The second instruction is store, to store value to memory. So for the left-hand side, it must be a memory reference by register or by an address. So we can store a register to memory, store a value to memory, and store a value from a memory reference to memory, something like that. So we have some form of use of the store instruction. And the most common use instruction are store a register to memory and store a value to memory. The third one is adjust instruction. Here just a synonym for add or subtract value from register. So you can adjust a register with a value, like you can do it in stack shipping, adding a stack pointer with some value to jump to your control area, like that. So when we implement the automation, so adjust can be converted to add or sub instruction, but by default it will be add instruction. A con instruction is the synonym for con or jump to a function. Here we can con by a register, like indirect con to a register reference, con by an address, and con to a value reference by an address, like we calling an entry in God table, for example. The last one is syscon instruction. So it just issue a system code, right? The NOP instruction is obvious, and so NOP is just no operation, and in ROP term it equivalent to rest. Just do nothing, just leave the stack. So now you have just six instruction. Now how to write the shell code in our defined intermediate language. So here we have some simple shell code. For example, ARM protect, we call memory protect on the writable address with the sign and with the flag. So on the ARM, on ARM architecture, it will equivalent to load the register 0 with writable address, register 1 with the sign, 2 with the flag, and register 7 with the mprotect system con. Here is 7D in hash, and then it's a syscall. Another example is execv/b/sa00. So you just repeat that process. Load R0 with the first argument, S1 second argument, 2 third argument, and syscall number go to register 7. It's a syscall. When writing ROP shellcode, you most of the time you cannot know the let's say here either /bin/sa string in memory, so you can create it like a writable memory you can write to. So you just write the string /bin/sa to it first, and then make the con. So here we can do it with store string bin to writable and store string sa to writable +4, and then do the rest like previous code. So we can write the high-level wrapper from our intermediate language for, let's say, higher level compiler or high-level framework for ROP shellcode. Here we can write a wrapper for syscall with syscall number and any argument. So you can check, you can load first argument, go to R0, R1, R2, so on, and then load the syscall number to the R7, and finally con syscall. You can write the high-level wrapper for function con, like you load argument to register for argument. If there are more than 4 arguments, the 5th argument will go to stack, and at the last you con to the function address. That's on for the shellcode. You can write a wrapper for, let's say, sell the return from function con to some memory, or doing repeating write every 4 bytes to a memory region. So we have a shellcode, but it will not be usable if we don't have an automation tool to convert it from the shellcode to gadget and then payload. If just a language will not solve our problem. So here our implementation is called ROPMAP. Something to note about ROP automation. So you may know some of the available ROP automation toolkit, like DevLib for x86 architecture from Immunity, and like the tool called ROPEME WOP compiler from Dynamic, but it's not public. And in the toolkit, what they do formulate every instruction to expression, and then evaluate with the SMT or STP solver. Will be very complicated, and frankly, I don't have any experience with the solver. So to be not that, to do ROP automation, if you remember the third slide, that simple gadget, we can do automation with just simple gadget and no solver here. So our implementation, what we call the ROPMAP. Here we define the ROPMAP is just direct mapping from ROP instruction to assembly gadget. So, for example, from one ROP instruction to one or more assembly gadget. And what we will map to just to primitive gadget, what we call it the simple and short gadget, and most available in every binary. And another map we define here called chain map. In case there is no direct mapping from ROP instruction to assembly gadget, we will map it to another chain of ROP instruction. We'll show it later. So we will have a complete map from ROP instruction to assembly gadget or to another ROP instruction. Then we define engine to search and chain gadget together based on the map. So with the map, you can search for any gadget, chain them together, and finally generate the chain. And the last, we create a payload generator to generate the payload from the chain of gadget we found. So here I will show simple ROPMAP for load instruction. Idea here is simple. Let's say you want to load a register with a value. So available assembly gadget, we have a, let's say the instruction is move value to register, right? Or it can be a pop instruction to pop value from the stack to the register, or it can be the LDR instruction to load register from the stack. So for the load value to register, we have three. We can map to three gadget instruction. For the load register to register, similar, we can have three possible instructions like move register to register or add register register. For the loss register from reference, memory reference by register, we had LDR instruction. And the last one, you will be notice that for the last one, there will be no equivalent instruction in ARM architecture that will load value from memory referred by an address to register directly. So here we map it to two instructions. That the first one is load address value to a register, then we load the register from memory reference by register, which already mapped in our previous map. Huh?
Do you do liveness analysis and register allocation as well in the chaining?
We'll show it later. Yeah. For example, for the store instruction, it's just super instruction. So we will only have one ROP map for the store instruction. Yeah, to store a register to memory reference by a register. The rest is not available on ARM architecture. So we will map it to here. You will be noted that we just do the binary mapping. So one instruction, one ROP instruction will be mapped to most two instructions. So store, for store instruction, it can be mapped to a load and then a store. So, for example, to store a value to a memory referred by an address, we will do first load that value to a register and then store the register to memory address. So it will cover all possible scenario of use of our instruction here. So in order to convert from ROP shellcode or ROP instruction to chain of gadget, we build an engine called assembler engine to automatically search for the gadget and chain them together. So here we have assumption that binary we target had enough primitive gadget. Let's say like simple pop register, load register, con, whatever. So we just do those simple gadgets, but don't looking for complex gadget. And chaining the simple gadget is more easier than finding the complex gadget. So if you back to the previous slide here, it will be very difficult to find a gadget that do the instruction like the last instruction. You have to find a gadget with 5 or 6 instructions to do exactly what we saw here. So our approach is just first use our tool to search for a candidate, a list of possible gadgets. And then we will chain them together via what we call a pair matching, like left-hand side of this gadget matched with the right-hand side of this gadget, and left-hand side of this matched with the left-hand side of this. That's all. Yeah. And we also apply some very basic validation rule. Here is like operand matching, like register must be matched from the ROP instruction to the gadget. And we also do some tented register checking we saw later. So the first one is pair matching. Here we saw an example of the store instruction. So we want to perform store a value which is referred by address to the memory pointed by the target. So here we will find the last one, the last instruction will be str to store a value. So here we have str R0 to R4 plus 16. And in our candidate list, we find that there another instruction is pop R4 PC. So we know that we have to load the value of the target value to the register R4, right? So here we will match that two gadgets. It's a pair. So R4 plus 16 will be matched with R4 in previous instruction. So we have first pair match. Then we move up. We know that we have to load the value value to R0. So it can be used in store, last store instruction. And in our candidate list, we find there LDR R0 from R4 plus 4. So we will have a pair match here. Left-hand side, the R0 of the second instruction with the fourth instruction. So it match. And we know that the value of address must be loaded into register R4. So again, in our candidate list, we found that pop R4 PC, so it can be a match. So our tool will generate those gadgets, so a chain of gadgets for store instruction, right? And we also apply some instruction validation. Here, what we call just for example, for operand matching, it's obvious, right? For example, in the first instruction, we had the ROP instruction is load R6. So in our gadget chain, it must be an instruction that load the R6, like LDR R6. But here, we can see in the first chain, the last instruction will pop R6 from stack. So it changes our intended value. So it cannot be used. It's invalid, right? Another example for the check-in is store instruction. Here we want to store to memory refer by R1. And in our gadget chain, we found that there load R1 to load value to R1, so it's invalid, cannot be used. Just that simple, and we just do that simple, and it works on most of the case. It's not complete, it's not 100% complete, but let's say just 80% is enough, and it can save you a lot of time in exploit development. We will show. Here in an example of ROP shellcode to the gadget chain. Here we had the ROP shellcode for execv/bin/sa. So ROP code load R0 equivalent to the pop R0 PC. Load R1 is pop R1 load. So just very simple, just some pop instruction, and then finally the system call instruction. And you can see here in the chain, there are some instruction may be duplicated in terms of load in the register, right? But we don't care now. Now we have the gadget chain. It's a big improvement from nothing to a gadget chain automatically, but it's still not enough. If you have to do the payload manually, you still have to spend lots of time to put the right value on your payload, right? So here we create a payload generator with input from the ROP instruction, or it can be in a gadget instruction. It can be a constant value on stack with some constraint and value winding, what I will explain it later. And then we create the output if final payload you can use directly in the exploit. And it is noted that our payload generator is automatically but not optimized inside. So in order to do that, we do still some basic emulation for gadget instruction. Here we will emulate every single gadget, and only the stack related operation like pop register from the stack. So we just do that. And we perform the rollback, automatically rollback value to stack position So if you pop a register from the stack, so we must write your intended value to that position. The idea is just that simple. So in order to do that, we do a revert process. We will do the pair matching from the bottom up. So from the last gadget instruction up. And just do some simple math calculation like write to R4 plus 16 with value 10, then you will have on the stack, just subtract it. And we will do the value binding feedback to the next instruction. So if there is some duplication, the value is still correct. First, we do the revert matching. You can see here, for example, if you want to load register R0 from memory pointed by address, so you find the chain pop R40 and then load R0 from R4 plus 4. So you do the reverse from the last instruction back. So we have here the address must be matched with the R4 plus 4. In another word, R4 must be addressed minus 4, right? Then we travel back. So we have a pop R4 PC. So R4 plus 4 is matched with the R4, and so that value will be, let's say it will be propagate back. So we have R4 is address minus 4. That is our value on the stack. Next, we do the gadget emulation. So we will do it for every single gadget, and we'll repeat above step for every gadget. And just focus on stack related operation like pop, load, add, SP, like something like that. So first, initially we have a stack with the just junk value. We put it just junk value. And every register is free, is uninitialized. Then we execute the instruction here. For example, we had the instruction pop R2, 3, 7, and PC with the value binding, mean the value from the revert matching provided. So here we had the R2 must be 0 and R7 must be B in hash. So by executing the instruction, we will have, so it's just pop value from the stack. So we have R2 is junk, 3 junk plus 1, and 7 is junk plus 2. Next. So when we finish the execution of the instruction, we now write back the value to the stack. So here we had the value binding R2 is 0 and R7 is B in hash. So we search back for R2, it is junk, so we map to our stack and place 0 at the first position. We'll map back the R7 is B in hash, so junk plus 2 or the third position on the stack must be B in hash. The rest we don't care. We put with the junk value. So the final payload we have on the stack is 0, junk, and B. And for the output payload, we can have here just an example for previous ROP shellcode. Here is the execv/bin/sa with 00. So its output is the the ROP code, the gadget instruction, and then the payload. We have here gadget offset value, gadget offset and require value on stack. You can see here there are some duplication. So let's say the value of R1 is 0, and it is repeated from the first, the second instruction, and the fourth instruction. So at the end, when you issue the system call on the register, just be loaded with intended value. Okay, so now we will have a demo. In our tool, we can, let's say we have the assemble instruction command to assemble from the ROP instruction to a gadget chain. Like we want load R0 with value. So it will return the first gadget chain in a set of candidate. If you want to look in for more instruction to use, so you can do with search. So there are many gadget instruction can perform the same operation that load the R0 with a value. And you can do payload generation for that instruction, like load R0 with a value. So we have here a pop R0 PC instruction, and our payload will be gadget offset and the value. So you can use it in like high-level wrapper, right? You change the value dynamically. So you just change the value and regenerate final payload. Here we take an assemble So here is shell code to exploit buffer overflow bug on ARM architecture. For example, here we have our target is B0, 1200. So it's a writable memory address from linker of Android. So we just store our stub code to our target. So simple instruction, just store it. And then we do the mprotect system call here, load R0, R1, R2, R7. And actually there is another trick that we load the R4 with a value for stub code, prepare for stub code. And then issue a system call to call mprotect and turn the memory to readable, writable, and executable. And then we just jump to it and execute the stub code and the rest shell code. So we will generate the payload for this shell code payload. Wow. So we have here every ROP code will be translated to a ROP gadget, and then the payload, corresponding payload, we So here. So you can sell it to, let's say, a file like PLD. For example, here we had generated just in form of high-level wrapper of the payload. So you can choose to optimize it, like remove the duplication if you want to reduce the size of payload. Or you can change the value, like base value to runtime, to correct runtime value. Right? So you can do some optimization here or validation at it. It sometimes cannot work 100% out of the box. So it's good if you can review it. And then if you're done with your review, you can generate the final payload with the format command we have here, like to Python format. So just copy it to your Python exploit script. Right. You can generate it to the like string format, put in C code, for example, or even you can generate to binary format to put it directly to the payload. So here we already have a demo we recorded. Install it. To set the time, we need to run the Android emulator. Now here we show an example of generate the payload for the drop exploit for Android 3.2 with the gadget from dynamic linker. You know that linker is just a stated binary, just a small binary and small set of gadget. And in this example, I just don't want to use the gadget from libc to, as I don't want to use like just called system function from libc or mprotect function from libc. So we use the gadget from linker. So this is the same what we have. So So here we just write the payload to a binary file and copy it to demo. For demo exploit, we have so here we just have by shell. I reuse from other people. Then we have padding value. The payload will be padding plus drop A from, we will load the drop stop from the file provided in the argument call. So just run it. Just simple buffer overflow application. it crashed because we run in S3, and here you can see that it con to ARM protect with return value is 0. That means it finished successfully. And if we run it without S3, we will spawn a cell. So you can have your ROP payload for exploit just in just a minute. So it's still lots of things to improve. And for example, we have to optimize the output payload to reduce the duplication. For example, we can load multi-register in one instruction, for example. And here we don't support ARM in thumb-2 mode, just ARM and thumb, no thumb-2 mode. If we support the thumb-2 mode, we can be found more gadget. But actually, it's not necessary right now. We can extend the engine to support x86 and x86-64. Actually, it partially works right now. We can search for the gadget chain, but for the payload generation, it's still something to do. And we might add more interesting instruction for our ROP instruction set, like support the conditional jump or loop instruction. Finally, thank you. Any question?